Hi, now that we have seen some basic ensemble techniques, it's time for some action. So in this Jupyter notebook, I'll demonstrate some of these basic ensemble techniques which we just covered and show you how these improve our models and their accuracies or whatever is the output metric. So let's start. So what I've done before this video is I've created a folder where I've put 3 files, the Jupyter notebook which I'm using, and it has 2 data files, data_cleaned and train_cleaned. So data_cleaned is the Titanic data set, which I'll be using to demonstrate max voting, and train_cleaned is the regression example, which I'll touch later in this video. So let's start with Titanic video. So to start with, let me import the necessary libraries. So I import pandas and numpy, and I'll read the CSV file. So the file which I just showed, data_cleaned. So I'll read that in a data frame called data. So let's just check whether this is in line with our expectations. So there are 891 rows and 25 columns or 25 features. And let's just look at the file quickly. So when I look at the file, I can see features like age, fair, P class 1, P class 2. And it also has the dependent variable, which is survived. So let's separate survived from the list of features. So what I'm doing over here is just removing the survived feature from my data frame and creating a new variable y, which is just the survived variable. So I've separated independent and dependent variable, and now it is time for modeling. So in order to do this modeling, what I'm doing is first splitting my file into train and test. So I'm using train test split function from sklearn, and I've defined a random state which is 101, and I'm using stratified sampling. Right, so now we have the data set, it has been read, we have separated dependent and independent variables. So let's now build a few models and see their individual accuracies. So as we have covered logistic regression, k-nearest neighbors and decision trees, so I'll build 3 models with each of these kind of modeling. So let me import all of these 3. And let's start with logistic regression. So what I'm doing over here is I'm creating an instance called model 1. I'm fitting the model on train X and train Y. And I'm then predicting on valid X, which is just the normal way to do it. In order to look at the outcome, so I'm looking at the first 10 predictions from pred 1. And I'm also looking at the score on my validation set. So let's go ahead and run this. So as you can see, the individual predictions, so they are either 0 or 1. So the first 4 predictions are 0, the 5th one is 1. And the overall accuracy or the overall score from logistic regression is 0.7757. Right, so let's go ahead and now do the same thing with k nearest neighbors. And in this particular case, I'm using k as 5. So I'm picking k as 5 and running the same thing. So as you can see, now k nearest neighbors tell me that the first row, the prediction is actually 1, which was 0 in case of logistic regression. So I can already see different opinions coming from different models. And the overall accuracy score comes to 0.7399 in this particular case. So let's go ahead and do the third model, which is decision tree classifier. And here I have used max depth as 7. So the depth I've specified as 7. Everything else remains the same. And this time when you see the outcome, so you again see that decision tree has given the outcome 1 for my row, which was predicted as 0 by logistic regression. So there is difference of opinion coming. And now if you remember what we discussed, so in order to do classification, we can use a very simple technique, max voting. So let's go ahead and do that. So I'm importing mode from statistics. What I'm doing is I'm creating a numpy array called final_pred. And then I'm just appending that particular array with the mode of each of those 3 predictions which we did. So pred 1, pred 2 and pred 3. I'm taking mode of that, so which is essentially max voting. I'm appending that to final pred. So let's go ahead and do that. And finally, in order to see the accuracy score, I'm just importing that from sklearn and running that. So if you see, my initial accuracy score from each of these models were 0.7757, 0.7399 and 0.7713. So the maximum score I had was 0.7757. When I combined these three models using max voting, my final accuracy came out to be 0.7982. So my overall accuracy increased from these three models. So you can look at this for comparison's sake. So by using simple max pooling, we were able to increase the accuracy. And this was a very, very simple demonstration. So let's do the same thing for a regression problem, which in this particular case is going to be Big Mart sales problem. So again, we go and import the libraries. We import the dataset. So the train_clean dataset, which I showed you. In this particular dataset, there are 8,523 rows with 46 features. So you can see various features like item weight, item visibility, item MRP, and all the way up to, different types of supermarkets available. So again, let's just separate the X and Y components. So item outlet sales, I'll keep that as a separate variable, which is Y. Again, I'll do the test train split. In this particular case, I'm not doing any shuffling. And I'm again using three modeling techniques. So instead of logistic regression, which we used for classification, we'll use linear regression. And because k nearest neighbor and decision tree can both be applied for regression as well as classification, we'll use those two techniques. So let's use these three techniques to build our model. So again, very similar to what I did before. So I'm creating an instance called model 1 and I'm fitting the model on my train and validating it on my valid_x. So here are the top 10 predictions along with the overall score, which comes out to be 0.55. So this is linear regression. Let's do the same thing for k nearest neighbors. So in this particular instance, again, I have 10 predictions or just looking at them, and the score has come out to 0.50. And from decision tree, we get a score of 0.57. So we have built three models. All three of them have given us different scores. So 0.55, 0.50 and 0.57. So now what we'll do is we'll just append them, and let's start with simple averaging. So I'll just use the mean of predictions from each of these three models, append it to my final_pred, and then see what R square does that give me. So let's again create a simple NumPy array, final_pred, and I'm appending it with mean of pred1, pred2 and pred3. So when I go ahead and let's now import R square. So when I look at the R square, this has now come to 0.57. From, if you look at the previous scores were 0.555 in the first model, which was linear regression, 0.500, which was from k nearest neighbors, and 0.573. So we see some improvement. So the best model was 0.573. It has come to 0.576. So there is slight improvement. And that is probably because we used a very simple averaging technique, but there is definitely some improvement. So let's try out slightly better or more nuanced technique. So let's see what happens in case of weighted averaging. So again, I'm importing the libraries, I'm importing the data set. I go through the same steps, just look at the data set. Let's split X and Y. Again, I'm splitting them in train and test, and the same three models, so linear regression, k nearest neighbors and decision trees. So let us go ahead and run these three models. So I run linear regression, which gives me a R square of 0.55. Let's run k nearest neighbors, which gives me a R square of 0.50. And let's run the decision tree regression, which gives me a R square of 0.57. So we had seen these R squares before as well. And now instead of combining by using simple average, let me give it weight. So the first model and the third model are giving me better results. So I'll give them higher weights. Whereas the second model is only giving me 0.50. So I'll give it a lesser weight. So I basically use the same function mean, and I have just copied pred1 2 times, pred2 1 time, and pred3 2 times. So in effect, I'm giving them different weights. And with the final pred, I'll again run my R square. And this time my R square has improved to 0.5810. So we can see that weighted average has given us better result compared to simple averaging. So in case of simple averaging, my score was 0.576. So you can see that here. Whereas in case of weighted average, it has come to 0.581. So we have seen some improvement. And finally, let's look at rank averaging. So again, the initial steps remain same, where I am importing the data set. I am importing the libraries. Let's check the data set. Let's split X and Y. We import the test train split. And again, we are using the same three techniques. We had seen the score. So 0.555 from linear regression, 0.50 from k nearest neighbors, and 0.573 from decision trees. And now, in order to score them, so we'll need to first rank order them. So these are the three models. So what I am doing is basically scoring them into which are my best models. So here are my models sorted by rank. So I'm getting a rank of 0.50 as my first rank, 0.55 as second rank, and 0.57 as third rank. So let's go ahead and sort them. And now I'm getting the weights by dividing the rank by that sum of ranks. So you can see that my model 3 is getting the highest weight, which is 0.50. And I'm then using these weights to come up with the final prediction. And because these weights were already normalized, I don't need to do any division. And this is the final rank prediction which I get. And finally, we look at the R square using these final rank prediction. So the overall R square by using rank averaging comes out to be 0.5828, which is again better than what we saw in case of weighted averaging, which was better as compared to the normal averaging. So that was just a demonstration of how ensembling can give us better results. And as you saw, these techniques essentially combine basic models to give us better outcome. Thank you.